These are things you'll read. They tend to not be true. CX packet weights do not necessarily mean bad performance. Parallelism is definitely not bad. Things are getting kind of strange though. We have new weights in SQL Server. As of 2016, Service Pack 2, and 2017, Cumulative Update 3, we now have a new weight in town, CX Consumer weights, which used to, before 2016 Service Pack 2 and 2017 CU3, these weights still happened. They just all were called CXPACKET. So some of CXPACKET, some of the things in the weight stat CXPACKET have been taken out and put into a new weight type called CX Consumer. And this is to help us see what's going on inside of parallelism. If we're looking at a query plan, say it's running at DOP2, we will see operators that look like this in the plan. In reality, this is not what shows up in the plan. But in reality, a lot of the operators, not exactly all, some of the data access operators actually do implement parallelism within a single operator. But like this hash match operator, it really is like, imagine this being single threaded, right? Each of these is using one thread. They are running independently and outputting their data, and then the data gets gathered together in another operator. It gets consumed inside this gather streams operator. This is looking inside the gather streams operator up here. When we're picturing the gather streams operator, it actually has multiple things feeding data in, and they are called producers, and the operator is consuming it. And when we're seeing weights in here, if we are seeing consumer weights, if this guy is waiting, if the consumer is saying, they're feeding me data and I'm waiting for them to finish, they are not done sending me data yet, that is a CX consumer weight. If these guys who are sending the data over, if they are waiting on the consumer, if let's say so many things are sending data to the consumer that it's just like overwhelmed and steam is coming out of its head, and they actually cannot send their data over because it just is overwhelmed, that is now called a CX packet weight. So used to, in the old days, CX packet weight was either side waiting. Both of them waiting is called CX packet in older versions of SQL Server. In the new version, CX packet is just if this guy gets overwhelmed and it cannot even accept the data that we're sending it. That is written out on this slide. The idea behind this is that if the producer is waiting for consumers, if this guy over here is waiting on consumers, or sorry, it's so easy to get this wrong. If this guy is waiting on these guys and they're still sending data, that is less likely to be a problem. In fact, Microsoft says it's ignorable. I don't think it's ignorable, but there are some blog posts that were like, and they even made in execution plans like these weights don't show up. And I'm like, no, I actually want to see those weights. Because what if, like, here's my take on it. Like, what if one of these guys is done and the other guy had an unbalanced amount of work to do? Like, let's say this bird got like 50 times more work to do than the other one, and we're waiting on him and he's not done yet. Well, that's a problem, isn't it? If the work was distributed more evenly, maybe they'd both be done. So I think that the CX consumer weights, I do think it's interesting to look at and they can be useful. But it is totally true that if these guys are waiting, if the consumer is totally overwhelmed, yeah, I do want to care about those. So I do like that CX packet weights are more meaningful, but I actually care about both types. I do think it's good that they're separated. We're going to look at a little bit of demo of this. Do CX packet weights mean, like in the old days, if I see CX packet weights, should I change the max stop? Unfortunately, we have no idea which one is waiting in the old days with the CX packet weight. So the answer is maybe. Possibly we could. I do use it as part of my tuning, but it's really unclear because it's hard to know who is waiting. In the new days, if we have high C, it's a little more clear now. Now, this is very hard to remember, but when we're working with the query, if I do see high CX packet weights, likely lowering max stop may help. I would still test it. I wouldn't believe for sure, because as you're going to see, lowest weights does not always equal best performance, right? But if we, after SQL Server 2016 SP2 and SQL Server 2017, cumulative update, whatever, if you see high CX packet weights, it is an indication that maybe lowering DOP could help because we're overwhelming the one receiving the rows. So if fewer things send at the rows, maybe it'll be more efficient. if you still see high CX consumer weights, maybe they could be faster at a different DOP, maybe even raising the DOP, but it's still unclear. But it's worth looking at, okay, maybe we should be tuning this because they're taking a long time to send the data over. So here's my thought process. If there are high CX packet weights in a period, I want to know who's using the most CPU, what degree of parallelism are they getting, and are there any obvious problems in the plans that where it's just like, oh, look, we're doing a giant index scan there. I could probably make that faster with an index. Are there warnings in the plan? I will test changing the DOP, but I will look at other things as well. When I see high CX packet weights, I don't just only consider DOP changes. I want to look at the whole query plan as well. All right, so the latest question. So in a way to understand CX consumer and CX producer, I don't know if that's a comment or a question, so I may need you to clarify that one for me. Let's look at a demo of different DOPs and these weight stats. I have a little test harness I've created. If we go into the next demo, I do have my automatic NUMA on right now. My auto soft NUMA is allowed right now. So we're going to do CXPACKET. This is our final demo script on the consumer weights. This query is using maxstop 10. And this query is this is our small query doing the gender and the count star. It took 3 seconds that time at maxstop 10. Let's run it again. It has data in cache now, and it's back to 1 second. Kind of took up a lot of the memory for that other query. What we're going to do is we're going to measure the weights for our session. We got a big old gift in SQL Server 2016, which is the dmexec session weight stats dynamic management view. And this is super handy because we can figure out the weight stats for a session without having to run like an extended events trace or sample weight stats for the whole server. I can take a sample from this dynamic management view of what are the weights for my session ID right now. Then I can run some activity. Then I can take another sample, what are my weights right now for my session, and just do a diff and see what were my weights between the time I took these 2 samples when I was running this query. So I'm going to get this thing going. I'm going to make sure, yeah, I don't have actual execution plans on. That's good. And we'll talk through it as it runs. It doesn't take too long to run. What we're doing is we are running this in a loop, and we're starting at maxstop 10. And we're running this query at maxstop 10. I'm using dynamic SQL and a hint that I run it at maxstop 10, then I run it at maxstop 9, 8, 7, and so on. When it gets down to maxstop 1, it is going to be very slow and run for 47 seconds. While it's doing this, it's putting data into tables T1 and T2, and I can analyze this as it goes in another session. I am looking at the 2 tables and essentially just doing a diff of the weight. So we can see that when this ran at maxstop 10, the duration was 1.6 seconds, and here are the weight types it had. We had 15 seconds of CX consumer weights. That is supposedly the ignorable weight. We had 1.6 seconds of CX packet weight. That is the one that is still a problem. So in other words, we have CX consumer weights. That is the time all 10 cores are sending data into the parallelism gather, right? And the parallelism gather is saying, okay, keep sending, keep sending, keep sending. You're not done yet. That is the time for waiting on all of them added together. The CX packet weight is those threads giving them the data and being like, well, take more data, take more data. You're overwhelmed. So when we go down to 9 threads, notice that CX packet weight goes down. It's down just a little bit because we had fewer threads giving data into there. So it was able to consume it more efficiently. Our duration was actually a little better for maxstop 9. At using 10 cores, we were actually a little slower. Well, let's look at maxstop 8. Maxstop 8, here's the maxstop 8 group. CX packet weights are very similar, right? Our duration is also very similar. Our performance at 9 is really kind of the same as 8, right? CX consumer weights are down. It was able to gather the data a little more quickly. As we go down here, we see the weights change. And let's see, it's already down to 2. So at maxstop 2, here's the maxstop 2s. CX consumer weights were 6 seconds. CX packet waits are 3 seconds, our duration is 3. Now this is kind of a lot to take in. It finally did finish up at max stop 1. It's kind of a lot to take in a big list. So let's go into, this is my downloads folder. And I can, if you're interested in having these files, I don't think I've uploaded them, but if you'd like to see them, I could upload them to the course too. Let's go up here a little bit. Oh, I'm not actually, I need to go, this VM does not have Excel installed. So I do actually need to go to a place where I have Excel installed to show these to you. That is an important thing. But I have some charts set up where I just dropped this data in. I am not a master of Excel, but even I can do a pivot table every now and again. So we will get this guy out of full screen mode and pull this over. And here is what the data, this is on a past run. Here's what the data looks like. Oh, okay. If these would be nice, I'll upload the Excel sheets. You definitely get the scripts. You already have the scripts, but I'll upload the Excel sheets too. So here is the data for the query. This is called small query. And I ran this loop with automatic soft NUMA enabled and no automatic soft NUMA enabled and recorded all the info for it. For duration for this query, the dotted line is with automatic soft NUMA on, the hard line is with no soft NUMA. Notice that is really similar. The automatic soft NUMA for this query did not really change my performance, and that remained true for the other queries I've tested as well. It really is focused around more of a concurrency setting. One might think that, so on my hardware, right, we only have a single NUMA node on the hardware, but we do have like automatic soft, when automatic soft NUMA is grouping these, it's 5 cores per soft node. There's no dramatic performance decrease for auto soft NUMA when I go above 5. But looking at this data, what we want is we want the best performance for the lowest DOP, because we want to use the fewest resources. As we use higher DOP, our total CPU usage goes up. So where is the sweet spot here? Well, it kind of depends how picky we are. I mean, max stop 4, do we really want to go above max stop 4? Yeah, it gets a little faster, but we get really good perf at max stop 4. So that kind of looks like, oh, that's the lowest fast value here. I mean, even 3 and 2 are pretty darn good, to be honest, for this query. Well, what were the weights? Do the weights show? If we're just looking at the CX packet weights, what do they appear? What's if they aren't showing up for 2? Why are you not showing up for 2 here? Do I have you filtered in some way? Let's see what we've got here. And we have data for max stop 2. We should not see the CX packet weights at max stop 1, but we should see them for 2. Let's look at this here. And what are you doing? Are you just displaying funny Excel? Yeah, Excel just, I was like, they were there yesterday. Excel just didn't feel like showing those lines. Looking at the weights, this is a little complex because we've got the auto soft NUMA and the non, but they're very similar again. But at max stop 4, CX packet is the weight that we're now told we should, they're separated out, and we're told that CX consumer is kind of ignorable. Well, the CX packet is technically lower at max stop 9, right? But if I look at my duration, yeah, I guess my duration's kind of lower there, but I wouldn't pick this just based on that weight stat info. I want the lowest number that has great perf, and yeah, the weights are slightly higher there, but I think this CX consumer is helpful. See how this CX consumer line is going up? That is representing that the ones producing the data are taking longer, they're taking more resources to produce the data. I don't want the ones where CX consumer is higher on here because it's less efficient. I want the ones where I have a low, yes, I want low CX packet. It's not 0, but it's low. But I also want it before the CX consumer starts going up too much, just to save resources, because I don't want 9 query threads retrieving my data if it's pretty much just as fast with 4. So this is why I think it's still relevant to see CX consumer weights, even though they're supposedly not actionable. I really like knowing what they are because they tell me it's taking more resources to send the data in to be gathered together. And I really don't want to use more resources for that because I don't want to pay more licensing money. I have another query in the demo that's called the big query. And I have also run that against the same VM. These are both run against the VM that you're seeing today, the little single NUMA node VM. I have some more test data with multiple NUMA node that I'll show you in a minute. And for this larger query is just doing a lot more data access. For this larger query, for duration, it actually does continue to scale up to like 10, up to 9, and maybe max stop 7 is kind of my sweet spot here, but like it really, like somewhere around, we get below 100,000, 100 seconds here. The sweet spot is kind of 6 to 8, maybe is looking pretty good. Yeah, it is faster at 9. What do the wait stats look in there? Occasionally we get an anomalous sample. That's fairly normal to sometimes have an anomaly in there. But what we see in terms of the weights is CXPACKET is actually really low up till 9, and then CXPACKET only starts rising at 10. Well, okay, that's kind of useful, but CXCONSUMER weights, these guys in the top line, CXCONSUMER weights actually go down up until we get around 7, and then they kind of level off. And that means that we are waiting longer on getting the data. It is faster to get the data into the parallelism exchange around 7. And again, I think that's kind of useful, because if I was just using CXPACKET to tune this, it would really only tell me, well, we want something below 9. Well, what do we want? Okay, well, we really want where the CXCONSUMER weights aren't the highest. So again, I do think it's useful to see them. This is really for kind of fine-tuning individual queries. The most important thing remains the duration. So I've got some slides that dig into another example on this as well. I had a test instance in Azure that I created. And on my test instance, I was 2017 CU5. There are, by the way, a fix in CU4 in 2017 that fixes some anomalies in how these weights are reported. So I upgraded past that. And here's, it had my guest, and all this is in Azure, so I don't know exactly what the host is. I can see that the guest has 2 NUMA nodes and that there are 32 virtual processors each, and I can see the processor name that the guest reports, right? So I tested these queries at different DOPs there and looked at the weight stats and the duration with AutoSoft NUMA on and off. So for the small query on that hardware, we can see this is duration, and we've got AutoSoft NUMA and NUMA, and we can see very similarly the AutoSoft NUMA, even at very high DOPs, it is not slowing this down at all for this query. Well, what is the sweet spot here? It's kind of hard to tell because of the scale, because see how it's so much slower at max stop 1? We kind of lose all the variation in the line. The sweet spot for this, ignoring this graph now has max stop 1 cut off, so it doesn't skew the scale as much. There is some variation in here, but the sweet spot looks like we're getting down, around max stop 30, 31, 32. Our duration is nice and low, and it really isn't getting much lower down there, especially for the run when I had automatic soft NUMA on. Now, this is a cloud VM. Is the slower times on the orange line just due to there being other activity running on the same host? Maybe. So we don't know, right? But they're looking pretty darn similar there. But definitely it looks like if we want the lowest amount of cores that give us good performance, we're down to 400. This bar is 400 milliseconds. So basically this, I'm like, yeah, 400 milliseconds for this query might be good enough. So anywhere in this range might be the sweet spot. Well, what do our weights look like? Our weights look kind of interesting. CXCONSUMER is this group of weights. Let's go back. CXCONSUMER is this group of weights. CXPACKET is this group of weights. CXPACKET is the one who's still bad, right? CXPACKET starts going up around 15. So if we were just looking at these new CXPACKET weights, we would be like, oh, we shouldn't have maxed up above 15. CXCONSUMER weights go down. Now let's review who's who. When this guy waits, it's CXCONSUMER. When rows are still being produced, it's CXCONSUMER, supposedly ignorable. When these guys wait, hey, they can't take the rows I've produced, it's CXPACKET. So looking back at the graph, CXCONSUMER, supposedly ignorable, it gets down really, really low and then starts going up again. That is the rows the consumer saying, I'm waiting longer for rows to be produced. Actually, as our max stop goes up super high, and we actually have split out this work among so many threads, like we've got, in this case, what, 64 threads doing a few rows each. It is less efficient because we're like, oh, I'm fine. Come on. Okay, where are you? Bring it back. So that actually goes up pretty gradually. But it does, like, if we were to just look at this graph, it would look like the best duration would be like 14, 15, 16, right? Because our weights are both kind of the lowest right there. Well, that wasn't actually the fastest. So now I've highlighted this area based on the duration graph, right? The fastest ones are actually in here. If we just looked at the weights, we would not see the fastest duration. So it's close. It is helpful. It gets us near there, but still, it's not like we couldn't just set up a machine to be like, I want to tune the DOP to where the weights are the lowest. If we do, we will get close to the fastest query, but not exactly there. So just when you're tuning things, generally, even with the new weights, generally making CX packet weights go down is good, but you really want to be careful looking at the duration, because just you can't only tune by the weights. When we got the new weight types, I was like, oh, maybe you can. And then I looked at it in detail. I was like, no, you really can't. So for a larger query, run against the larger hardware with the 64 cores and the 2 NUMA nodes, here is the duration for the big query. And again, with max stop 1, we really skew the graph. But notice that our fast times for this query are around 100 seconds, not 500 milliseconds. This query is on a different scale. Getting the max stop 1 off the graph to change the scale, the sweet spot for this, like the place where it's fastest, is between max stop 16 and max stop 26. That's where we're actually getting the best performance, whether or not we have automatic soft NUMA on. Looking at the weight stats for it, the weight stats for it actually look really good around what? Max stop 10, 11, 12, max stop 13. Max stop 13, both kinds of weights are low. Our CX packet, the bad weight, starts going up as our weights get higher, right? So as our degree of parallelism increases for this query, we start overwhelming that consumer. We have so many cores sending a lot of data to that consumer, it just can't combine them fast enough, which is really interesting, right? Here is our actual sweet spot for best performance here. Now, if we go back to the duration graph, on this one, notice that it's not like it gets a lot slower as our DOP gets higher. It's about the same speed, but we do see that our weights get higher at high DOP. So this is a case where the weight graph looks kind of bad. It looks like, oh, it must be slower here because as my DOP increases, I get more weights, and they are the CX packet. That's the yellow line is CX packet with NUMA. The gray line is CX packet with AutoSoft NUMA. But our duration doesn't get worse and worse and worse, right? Just our weights do. So higher weights doesn't always mean slower, and our sweet spot for the duration here isn't exactly at the lowest point. It's actually at a point where the weights are starting to go up. In other words, don't drive yourself nuts tuning to get rid of CX packet weights, either with the new weights or the old weights. Having some CX packet weights may be fine. As you are tuning a query, it may be useful to be able to see, oh, which kind of weight is it? Is it the weight of like, oh, you're sending me more rows than I can handle? That is CX packet weights. Or is it the weight of, oh, I'm still waiting for you to send me, like, fine, keep sending me rows, keep sending, like, why are you so slow sending the rows? That's CX consumer. I think it can be very good for fine tuning, and that both weights are useful. I would not obsess over them. I would obsess more over query duration than over these. If we do have high CX packet weights after SQL Server 2016 SP2 and after, let me go back to the graph here. If we have high CX packet weights here in the new weight, when we also have CX consumer, that's 2016 SP2, that is a sign that lower DOP may be better. So this graph does make sense with what the advice from Microsoft is. Here I have high CX packet weights. My query didn't get slower, but I'm using more resources than I need. So yes, a lower DOP would be better for my workload, right? Even though my query didn't get slower, I think that's right. And I know this stuff is super confusing, so if you got questions about it, feel free. So I think they're both useful. I also think automatic soft NUMA is very useful. And I think it's actually good that we didn't see different performance for it in my testing, because what I'm testing is not a busy workload. What I'm testing is just one query. And this is helping with those shared data structures as we have tons more and more queries running in our system. So it's helping us avoid weird little problems we can get from spin lock contention on internal data structures, which I'm not going to see just running one query in isolation. So it's good that we saw pretty consistent results with it on and with it off. That is what I wanted to see there.